This is just a real quick model that I built of the first Type 2 engine. So it's just got a stand. It's two coffee lids, right? And then a nail through the center and a nail here. And what this does is this spins, right? This spins around, and when it hits an anvil, then it transfers the force into the spacecraft, right? And it continues to spin. And the spinning causes it to swing out. So if it's damaged, then that gets replaced. Unlike in a rocket where you have 9 to 15 seconds of fuel and then it's gone, you're just carrying an extra hammer, and you can increase your speed by cumulative acceleration. Now, this is just the first model, right? So I only had one hammer, and then I added 4. So this would have 1 on each side here, and that would give it balance as it spun. And this is giving you the force net. So your speed as it accumulates is equal to the force net of each impact times the RPM times 4 times the number of hammers or fans. And this is going to be a rigid disc with an electric motor. And as I said, these are just free spinning. Now, for the vector warp, it's just velocity times gravity, and this is this second one is a coordinate on the gravity. And I'll show you why in a second. But for the hammer now, from here, from the motor to the point where the hammer is attached is radius 1, and then from here to here is radius 2. And we do that because the circumference equals the distance and the rotation equals the time. So 1 rotation per minute over or under the circumference is equal to the speed, right? So the speed increases as the circumference increases. And for it to swing out, so the force is going to be equal to the mass times the speed, right? And the mass is the mass of the hammer. Now this 1, 2, 3, 4, 5 is the speeds, right? So these increase. And if this is a line segment AB, then the energy of point A is less than the energy of point B. And so that causes the entire physical object to swing out, right? So the highest energy is here, and it causes everything to pull out. That's that centrifugal force. So the E of A is less than the E of B, and it goes that way, right? Now, with gravity, you get the same thing. The potential energy of A and the potential energy of B in a line segment. The potential energy of A is less than the potential energy of B, so it falls. And all of the gravity is potential energy, right? And that's an R2 curvature. So it increases as it comes down. It's higher energy at the bottom, less energy up higher, based on the R2 curvature. And the rate is the mass. That's the normal rate. But when you have vector warp, you're multiplying exactly that potential energy at some or at all coordinates, but you select one when you do gravity times velocity equals vector warp, right? And so your graph gives you time, that's wavelength, by volume, right? Space-time. And so your vector warp increases here, and that gives you a polarity. So you get positive and negative potential energy, right? And that causes warp and causes your spacecraft to continue moving in the direction that it's going forever, the first law of motion. Right now, for For an object like this, or a spacecraft, or an airplane, like we can do a transition and put these motors onto an airplane, right? If it's really high up in the atmosphere, then it runs out of air. It could switch over to these and start flying into space, because these allow you to fly in space. But because of this, as you increase your height, your altitude, then the gravity is less, and that's the same as the normal gravity equation, right? That's the same as the normal gravity equation, right? As you increase your distance from the mass 1, then gravity decreases. So for a non-mass ejecting engine like this, that translates to a higher and higher force net as you raise in your altitude, right? So if you're going straight up, then your speed is actually increasing as you go higher